Hello, we're the Resilient Edge Cloud Group. Welcome to our final presentation. Our team members consist of Haider, James, Lakshya, Tanushree, and Shreya. Our problems, over the past 10 weeks, we've explored the problem of running neural networks on mobile devices. Neural networks are becoming increasingly complex, and so thus running them on mobile devices is becoming increasingly difficult due to processor and power limitations. A viable solution to this is mobile edge computing. What mobile edge computing is it's a network architecture that allows mobile devices to access edge servers computation and request jobs so that they can process things faster. And so why is this really a problem? This is a problem because we want lower latency on processing so that it allows for applications such as vehicular self-driving and image classification run faster on mobile devices.
So as shown in this diagram, there are first the cloud servers, which store a lot of data and perform tasks. And then we find the mobile edge devices or MECs, which is the one of our endpoints. And then come the mobile devices. What we're focusing on is the connection between the mobile devices and the edges, the red circles there. So what these mobile devices have artificial intelligence models within them. And along with the prediction given by this model, we get another value which represents its confidence on that prediction. And if the confidence doesn't meet a certain threshold criterion, it asks the edge device for help because the edge has more computational power and can do the task better. But this is at the cost of some time. So we measure the total time taken to perform the task for every data point. And in specific, the question we're trying to ask is, as you vary the threshold, how does the average latency change over the data set? So this is how our experimental setup looks. There is a mobile device which is at one node that gets data, which in our case is an image, and tries to label it or get a prediction. And if it doesn't satisfy the threshold criterion I mentioned, it sends a help request to the edge, which is at another node, and the edge performs the task and sends its prediction back to the mobile device.
Okay, so for our data set and models, first for the data set, we use the CFAR 10 data set, and it has 10 classes. These are all the classes that it uses, that it gives the models to classify. It has 60,000 total images, and we only use 10,000 when testing. And then for our models, for the most part, we use MobileNet v2, but we also use DenseNet slightly. So for our findings, these are baseline findings. For the baseline findings, we use MobileNet v2 on the smaller device. And then because we wanted a high accuracy on the edge device and we weren't able to achieve that on our own by training the model, we just switched to an Oracle, which knows the answer. Like it knows what the image is automatically. Our time synchronization protocol, we use PTP, which synchronizes the time of the two nodes in our system to within 15 nanoseconds. And yeah, so these are our baseline results. As you can see, the greater accuracy that you demand, the higher the latency is. And this is a graph of the total times that it would ask the edge device for help. So as you can see, when it requires like relatively low confidence, under 25% or whatever, it doesn't even ask the edge device for help. But as you increase the threshold for the confidence, then it starts asking for help. This is our first real experiment that we ran to simulate a real world scenario better, where we limited the CPU speed of the mobile device to a similar level as real mobile devices. And we also implemented a network delay of 8 milliseconds with a variability of 3 milliseconds in it to simulate real network speeds and inconsistencies in real networks. As you can see here, it's not quite as clear whether or not as you it specifically, as you demand more accuracy, the latency increases, the points are much more variable in a real world scenario, and it's a slightly more complex problem. And this is also another graph of the of just help requests and versus threshold.
All right, so our second experience is implementing the queue in the server. What queue does is you whenever you send an image to the edge, it would store it in order, and it will process the image classification by the order it receives. So while like the mobile sends the image over to the edge, it would the mobile devices will still continue to inference the next image, but and while like it can also wait for the edge responses. And as you can see, the range of the latency would just be around 7 to 12 milliseconds. And the graph doesn't seem like doesn't look exactly the same as the baseline experience, since like the queue would depend like the image classification from the edge. So our third experience is out of distribution. This one, in this case, we thought it would be a good case, since like mobile will have like the less capability of the class, meaning like it knows like the less classes of image. And we added an extra class called confuse, where like the mobile would classify the image to the confused class if it recognized if it's an unknown class. Then we would send over the confused class to the edge, or also we would also send when it doesn't meet the threshold. Then the range of the latency becomes 2.5 to 5 milliseconds. As you can see, the latency gets lower because like mobile knows like the less classes, and the time of the inference will also decrease. And as the threshold increases, it would send over more to the edge node, and the accuracy will also increase.
Okay, so now we go to the conclusion slide. So what have we learned throughout these experiments, right? So first we can talk about how implementing a threshold changes our behavior of the graph. So first of all, we realized that implementing a threshold causes lower latency inference than using only an edge device. However, on the other hand, it also gives us a higher accuracy inference than using only the mobile device. So that's when the trade-off comes in between the edge and mobile, lower accuracy versus higher accuracy versus lower latency. What do we want? Next, emulating real life by restricting the CPU speed and network delays has a high impact on latency, as we saw through the graphs. Finally, introducing parallelization and multi-threading during inference allows for lower latency and quicker predictions, as we also saw through the graphs. Okay, so now finally we can move on to the next steps. So what are we going to do? We're going to continue to emulate better real life scenarios, automate testing and data collection, and then use different methods such as early exiting and split computing in order to test our scenarios. We can have multiple clients and servers and different queuing policies to make the process more real worldly. We'd just like to acknowledge our sponsors, N versus Capital, Professor Servate, the other professors, and the National Science Foundation for a grant. Thank you.